also equal to each other, but none of this angle equal to 90 degrees. So it's more like you applying a shear force along all the alpha, beta, gamma direction, or the x, y, z direction. So let that tilt it. Let the lattice structure tilt it. So in this case, for the rhombohedral case, you can only use the simple structure. So that means the simple rhombohedral structure, there's only one type of unit cell associated with that, okay? So, and the other three types, now we introduce four types, right? The cubic one, tetragonal one, and the orthorhombic. These three are nearly identical. The only difference is cubic one has all three unit lengths are equal to each other. Tetragonal one, two equal to each other. And then the orthorhombic, all the three are different. Okay, A not equal to B, not equal to C. Rhombohedral is a bit different. It's more like a tilting. You applying the shear force. And then the other three types, one very special case, but very useful. Okay, that's as useful as the cubic one. It's called the hexagonal. Okay, because in nature, many type of metal or even ceramics, they can occupy the space very efficiently using either the cubic structure or using the hexagonal structure. But the hexagonal structure is more, it's kind of like more difficult to understand. One way to represent the hexagonal structure is, you can think about that. A equal to B, but not equal to C. Okay, so easy to understand, right? A, B equal to each other, but the Z direction, the length could be longer. Think about that way, okay? And alpha and beta equal to 90 degrees, but because that one is hexagonal structure, the other angle, gamma, equals not to 90 degrees, equal to 120 degrees. Okay, so think about that. Or another easier way you can think about the hexagonal structure, you can think about using this tetragonal structure. Okay, think about that. If you think about putting three tetragonal cubic structure, stacking them together, see, take a look. This one is a tetragonal, right? Okay, because A equal to B, but not equal to C. If you have three of these tetragonal cubic unit cell, but you do not repeat them 90 degrees along the x, y, and the z direction, but rotate it 120 degrees, then you will get that one, right? You can get this unit cell, and then you rotate 120 degrees again, you get the third one. By combining them together, you get the hexagonal structure. How about that? So that's a bit more complex than all the other. Hexagonal is complex. Okay, so, but you know, there's only one simple cube, there's only simple hexagonal patterns that one can be stacked. So hexagonal one is quite a bit different. Later, I'm going to compare. Okay, I'm going to give you examples about the hexagonal cubic cell, and extending on that one, you can also think about the monoclinic one. So that means A, B, C not equal to each other. Alpha, beta still equals to 90 degrees, but the beta does not equal to 90 degrees. So that means you tilt a tetragonal one only along the beta direction. Okay, so it's kind of like a tilted structure. So in this case, in the monoclinic one, you can actually occupy the space by using two different types. One is a simple one is a base-centered one. Okay, and finally, another very special case is called the triclinic one. So all the parameters are not equal to each other. So all the three basic lengths and all the three different angles not equal to each other. Yes?
Why isn't the hexagonal considered to be base-centered?
You mean here?
No, why isn't the hexagonal why is it considered simple, not base-centered?
Okay, so
because the most basic one is not.
Think about that way. Indeed, if you think about the unit cell, okay, several different ways you can think about the hexagonal. Okay, one way is to use, we call that an enlarged unit cell. Okay, it's like this. Think about that one. Okay, but indeed, the smallest unit is not that. Smallest unit is still this one, right? But if you want to repeat, you need to tilt it. Think about that. Okay, so therefore, it's kind of like a combination of this tetragonal one and the hexagonal one. Okay, there's another way to representing the hexagonal one. Later you will see that for hexagonal one, you can also think about stacking like a, hexagonal order. Let me show you that one. Okay, that's a good question. Because the hexagonal one is more difficult to understand, but we can think about this way. There's another way to think about the hexagonal, but this time close-packed hexagonal. We call that HCP structure. Okay? In these times, you can think about, you have 6 atoms packing at the bottom layer. Okay? And then on top of that one, you can put 3 other atoms directly above them. Okay, and then above, on the very first layer, you put another 6 layers. This layer, the position of the spheres on the top layer and on the bottom layer, they exactly equal to each other. Okay, they're exactly the same location. This one is the same one this. This one corresponding to that. Okay, so that's another way to representing the hexagonal structure. But I want to mention that the hexagonal structure, if you think about one atom, how many atoms immediately surrounding that one? If you think one atom, how many atoms immediately surrounding that one? 6, yes. So, but based on this representation, okay, if you think about that one, it's different. Okay, so I should say that the smallest repeating unit in the hexagonal lattice is not this. This one is larger than the unit cell of a hexagonal lattice structure. The smallest one is this. It's still like the tetragonal one. But you repeat it, you need to tilt that one 120 degrees and then 120 degrees again. Okay, that makes a kind of like a repeating unit. Okay, if you repeat that, this structure along the x direction and then along the other direction, you can get a repeating crystal structure. Okay, so anyhow, hexagonal structure is important, but not the major thing in this class. Okay, I won't talk much about that one. The only thing I want to show you later on is compare with a hexagonal close-packed structure with the FCC structure. Okay, but if you, it's not required actually. You do not need to remember all these 14 different type of unit cells. Even for me, I cannot remember all of that. Okay, but the most important thing you need to know is the basic cubic types. Okay, so the face center, the simple, and the body center. So these 3 types are very useful. Okay? So, but anyhow, based on the Bravais theory, we only need 14. Okay? We only need 14 different unit cells. We can build all the crystals available in the world. Okay? So, so based on that, then the reason why, as I mentioned, we are mostly interested only in 3 different types of crystal structure. One is a body-centered qubit, one is the face-centered qubit, and one is hexagonal close-packed. That's why I want to mention that, okay, you need to kind of like distinguish. The simple hexagonal cubic cell is different than the hexagonal close-packed structure. Okay, this one is more densely packed. The atoms in the hexagonal close-packed structure is more densely packed than that. I will tell you why later on. Okay. So, but anyhow, the sun. Today I want to mostly focus on one is FCC structure, one is a simple cubic structure because this one is the most simplest case, right? So we will first discuss this one, and then we will discuss the body-centered, face-centered, and then go to the hexagonal type, but the atoms are more close-packed. We call that hexagonal close-packed crystal structure because these three types accounts for about 90% of all the metal crystal structures available. Okay, BCC, FCC, and HCP. Okay, these are three important ones. But the most important, I should say, should be the FCC and the BCC. HCP is, important, but as I mentioned, the hexagonal structure is kind of, we do not have time. We do not have time to really consider that. Yes.
Can you go forward a slide? Why, is there a reason why 90% of them is just only those three? Are those like the most three stable or something?
The question is why 90% of the metals occupy using these three different types, okay? That's a good question. Today you will learn that BCC structure, I told you already, what the packing density. How much space will be occupied by the atoms? 6 to 8%, right? We will demonstrate that one today. We will do calculation. FCC, remember the number I told you? 74%. That's the highest one we can get. HCP, once again, is a close-packed structure, another 74%. Okay, 74% is the most efficient usage of the space by spherical particle, by the spherical atoms. Okay? So why that is because these three are the top three most efficient usage of the space. Okay, when you packing atoms, they always try to use space as much as they can. Okay, but don't forget, they try to reduce their repulsion. Okay, you cannot put two atoms too close to each other. Otherwise, there's a repulsion force, right? There's a repulsive force between their electron clouds and between their nuclei will repel them. So there's the final stable crystal structure is because of the compromise of the over energy. The over energy of the crystal is the lowest. Okay, so that's the reason why that. If you think about the other type, see for example, if we think about why not they take the simple cubic structure? Why not they take the why not they took the tetragonal structure? The reason for that is because these three structures are the most efficient usage of the space. Okay, the atoms are most close packed. Okay, so as I mentioned, hexagonal close packed, or we call that HCP structure, is a denser version. If we compare that with the hexagonal packing, the HCP structure or hexagonal close packed structure is the atoms are more densely packed than the traditional simple hexagonal one. Okay, but I do not have time. I do not have time to really go to the details by calculating that one. But to answer the question, the previous question, another way to think about that is this way. If you think about answer your question, okay? If you think about the hexagonal close packed one, if you compare this one is a hexagonal close packed. We call that HCP structure. If you compare this one from that one, what's the difference? Take a look. What's the difference? You have the middle layer, right? Take a look. Take a look one more time. This is a hexagonal close packed. That one is hexagonal one. The only difference is what? The only difference is in between. There's a interplane, right? There's another plane that has three atoms. These three atoms can be packed inside this enlarged unit cell. Okay? So therefore, the basic structure of the HCP structure is still based on that, right? The only difference is by using this basic arrangement, but if you put more atoms in between the basic structure, the basic hexagonal structure, you get more close pack. Using this kind of arrangement, you can get 74% of usage of the space. As I mentioned, there's a highest volume you can occupy that can be occupied by the atoms. Okay, not another crystal structure. The packing density of the atoms can be above 74%. But there's one assumption here. What do you guys think? What assumption? Why, or only by assuming that there's something you need to be assumed, then the highest occupation of the space is 74%. What assumption? Think about that. What is the assumption? Yes?
Yeah, spherical?
Yeah, the atom need to be spherical, okay? So give me one possibility. If the atoms are not spherical, the space can be more than 74%. What kind of think about that one. Can you get 100% of the space by changing the atom if you have another shape of atom?
If
What do you think?
there were squares, maybe?
More squares. Think about the cubes. If you think about the stacking cubes, you can occupy all the space. You can get 100%, right? Or if you say there is a very interesting discovery published not long ago, about 15 years ago, by a few physicists in Princeton University. What they do, they did another experiment. You know they use what? They use M&M, okay? Using those kind of ellipsoids. Okay, guess if the highest volume fraction can be occupied by the M&M, those kind of ellipsoids, can they occupy more space than 74%? Or lower than 74%? If they're elliptical shape, not spherical. Spherical, 74% is the maximum. What do you say? If you use elliptical atoms, can they occupy more space or less space?
Less.
More. They can get about 89%. Okay. So think about that. So think about they are more efficient in using the space. Yes.
So which atoms are elliptical shape?
No, you can always think about the atoms are spherical shape. There's more like a physical. Those are physicists, okay? They always try to build up some weird model, as an engineer, they are thinking about the limit. They are thinking out of the limit, I should say. So there's atoms, almost all the atoms are spherical. We think them that they are spherical shape, okay? But don't forget, they can actually use like a millimeter scale or centimeter scale of M candies as a model system to study the space occupation. Think about that one, okay? Yeah, those kind of, like placelets like, M&M candies, yeah. So they're using that one to study the space and occupation. But anyhow, that's kind of like let you guys think about 74% is the most close packed structure uses spherical atoms, okay? So now let's think about one by one, okay? Let's think about the simple cubic one first. Simple cubic is very simple, right? So that means you have, let's take a look. Oh, that should have some, so please be
To
quiet.
explain the volume and structure of the output,
Is that okay?
we assume that the atoms are spherical. The spherical atoms can be packed together in different arrangements. Some arrangements are more efficient ways of packing spheres than others. Simple cubic packing is 54% efficient. 54% of the space is occupied by atoms, while 46% is empty space.
These are empty
This is the
space.
first layer of the crystal with its atoms arranged in simple cubic packing. Click on the second layer button to see how the second layer stacks in simple cubic packing.
So second layer of the cubic stacking is what? It's just on top of the first layer, exact the same location, right? So how about the third layer? Same thing, right? So that's, okay, so then the second layer,
The second layer of atoms stacks directly on top of the first layer. Click on the third link.